Thank you very much. Thanks for the invitation. And so you might have noticed that I cheated here a tiny little bit in the sense that the title I submitted had an extra little bit. It was growing maps face by face and applications to flips. But okay, that was a sort of a bit ambitious as an idea of a talk, and I've decided that, well, this is the last talk of the morning. Maybe it's better in principle to take it slow, and this will be a bit more relaxing. I'd rather not rush through everything in order to show you applications. Also, given that, as a matter of fact, so flips on planar maps were my motivation for this problem, which is done in joint work with Alessandra Caraceni of the University of Rome and the University of Bath. But I think the problem stands on its own, and we have given other talks about how it relates to flips, and since in this age talks are usually recorded, you can actually find that online. So in case you're curious, you can Google it, and all I kept of the part about flips is this background, which hopefully might make you a bit curious about what the deal is. And so unless we're in the unlikely event that I finish quite early, I won't say anything more about flips on planar maps. But I will say quite a lot more about growing maps face by face. Now here I was a bit generic with this title. I went with maps, and we'll explore this idea in terms of maps in a few different directions. But I thought we might start with something that will be sort of a warm-up exercise, let's say for us, that is start in the coziest place ever that we know in terms of maps, that is with quadrangulations of the sphere. And so I'll start with my set Qn being the set of all quadrangulations of the sphere rooted with n faces, which to me, I will refer to this as having size n. All right, so another tiny comment is that since I knew this talk was going to be towards the end of the week, I was banking on the fact that most things that will appear would have already been defined by someone. Plus, I'll be sort of relying on the pictures for people who are not super familiar with these objects to hopefully just remind you what these things are, but please interrupt me if ever it's really not clear what kind of objects I'm talking about, and I'm happy to try to give you definitions. So in particular, I'll just say this kind of thing is a quadrangulation of size n. Great. So suppose we want to sample a uniform random quadrangulation of size n. Of course, we can do that. And to start with, we know a lot, and in particular, we can do enumeration since start. We know how many quadrangulations of size n there are. If I wanted to draw one uniformly at random, perhaps making a list of all possible quadrangulations is not the great idea ever, given that their number is exponential in n. But there are definitely better ways to draw a quadrangulation at random, which many people in the audience would know and would know better than me. And one of the reasons why we have better ways is the link that's being talked about multiple times now between quadrangulations and the world of trees. So here you're going to see sort of my personal rendition of a version of the Scheffer bijection, which draws this, let's say, bridge between the world of quadrangulations and the world of plane trees. So given a pointed quadrangulation, you can get corresponding plane tree of size n, where in this case I will mean size n means with n edges. Each edge corresponds to a face of the quadrangulation, and if you want to recover the quadrangulation, you need some labels on the tree. And now what will be convenient for me is to see these labels instead of as labels of the vertices that would carry a bit more significance in terms of the metric of the quadrangulation. I will just think of these corresponding plane trees as being 3-colored in terms of their edges. So each edge is colored one of 3 possible colors, which by no reason at all, I'm calling plus, minus, and equal. So, okay, right. So as a matter of fact, if I wanted to recover my quadrangulation fully from the object on the right, I need an extra plus, minus 1 that is going to give me the direction of the root edge. And so as a matter of fact, it will be convenient for us to think of the Scheffer bijection as sort of being 2 to n plus 2 correspondence between the set of quadrangulations of size n and the set of 3-colored plane trees of size n, where n plus 2 is given by the pointing and the 2 by this extra spin that we need for the direction of the root edge. This is my introduction to this link. Very well, so since we have this, if we're able to sample plane trees, then we're able to sample quadrangulations. And the thing is, we're definitely able to sample plane trees. And we'll comment a little bit on that in what follows. But what I want to do in terms of sampling quadrangulations is actually something quite specific. What I want to do is not just sample a uniform quadrangulation of size n. I want an iterative construction that allows me, given a uniform quadrangulation of size n, to obtain in a coupled way a uniform quadrangulation of size n plus 1, which is obtained from the smaller quadrangulation by sort of adding a face somewhere. And let me be more specific than that. So I will define for you an operation which I will call collapsing a face. So if I have a face of my quadrangulation and diagonal, so 2 opposite corners of that face that are corners of 2 different vertices, then I can collapse that face along that diagonal by sort of just identifying the 2 vertices of that diagonal and gluing the boundary to itself. So something like this, right? This for me is a face collapse, and I will call it the inverse operation of a face collapse, growing a face at that location. All right, as a matter of fact, I should be maybe a tiny bit more precise in the sense that here, for example, this face can be collapsed in 2 ways. It has 2 diagonals you can use to collapse it. But that is not true for all faces of the quadrangulation, because in particular, for example, so some faces have 4 vertices like the one before, some faces have 3 vertices. If a face has 3 vertices, I need to collapse it along the one diagonal that joins different vertices. And then I can also collapse this face if I want, and what I obtain is that. So this to me is the definition of a face collapse. And now we can define what I mean by a uniform growth scheme for quadrangulations. That is a way to couple for each n a uniform quadrangulation Qn of size n with a uniform quadrangulation Qn plus 1 of size n plus 1 in such a way that always the smaller quadrangulation is obtained by the largest via face collapse. And you can think of this coupling as something that reduces uniform quadrangulations to uniform quadrangulations, or if you prefer, you can think of the inverse of the phase collapse, and you can use it to grow uniform quadrangulations by adding a phase. Okay? Now, just to finish with something even a little bit more precise, let's set up a bit of notation. If you want, so what is this coupling? I could express it as just a collection of functions, fn. They take an input, a quadrangulation of size n plus 1 and one of size n. And what I think of fn as being is the probability of my smaller uniform quadrangulation qn being qn prime, given that the larger one is q. So what I ask of this collection of functions is that, well, the functions are non-zero only if the two quadrangulations differ by a phase collapse. The other thing I need to ask is for this to indeed be a probability. So if I sum over q prime over the smaller quadrangulations, the sum of the fn's needs to be 1. And the last thing I need to ask for is for this to indeed be a coupling between uniform quadrangulations. So essentially, if I sum over all the possible larger quadrangulations, the probability of a uniform quadrangulation being equal to q, so 1 over qn plus 1, and I multiply by the probability of obtaining q prime, I need to obtain the probability of having a uniform quadrangulation be q prime, that is 1 over cardinality of qn. So equivalently, I will think of growth schemes as being collections of functions with these properties. And I've called these properties 1q, 2q, 3q, in the sense that, of course, I can have uniform growth schemes for all sorts of different classes of trees and planar maps, and for potentially different operations other than phase collapses. All right. Now, let's take a small step back. Of course, this idea of growth schemes and of growing, iteratively building uniform objects is not new at all. And many of you might be thinking of perhaps the most classical of growth schemes for trees, which is Remy's algorithm, right? Which is a growth scheme for binary trees with a very simple growth or reduction operation that is very local and super, super nice probabilities, essentially. I won't go into Remy's algorithm really, because it turns out that that operation is not quite what I need in order to obtain the growth schemes that I want for quadrangulations. But notice that, for example, this would indeed be a good way to sample plane trees efficiently. You can just grow them iteratively with Remy's algorithm if you want. So I will continue with some examples. I should mention here that this slide is not going to be complete at all. So if any of you, for example, have done work on related things and it's not mentioned, I'm sorry, but I'd be very, very happy to talk to you about it. In any case, another example is a very, very nice paper by Lokschak and Winkler from 2004 that gives you a growth scheme for D-array trees, essentially. And I won't talk more about this for the opposite reason, that is that this will be heavily featured in the following parts of the talk. And I wanted to also mention, for example, just to show that, I mean, there is still definitely interest in this sort of building scheme for random sampling. For example, there's a very recent paper by Jean-François Marquer that does another growth scheme for D-array trees. That's more of a generalization of Remy's algorithm for binary tree, more similar. And to finish with this slide about context, it's also not the first time that growth schemes have been considered for maps or quadrangulations in particular. There's also this nice paper by Jérémy Bettinelli from 2014 that does, with a very bijective approach, grow uniform random quadrangulations. But let me make one comment about the difference between that and what we're doing here. So his growth operations consist indeed in adding a face, but also in making a cut along a path, essentially, opening up the quadrangulation, adding a face, and then re-gluing that hole that's been created in a bit of a rotated way. So it's not as local an operation as what I'm actually looking for. And for the applications to flips, for example, it's very important that the growth operation is local. So this one would not have worked for the application I had in mind. So very good. I promised that we do quadrangulations sort of as a warm-up exercise. So this being said, let's bring our two worlds back up. It's quite natural that we would, of course, try to obtain a growth scheme for quadrangulations by exploiting the fact of being able to build growth schemes for trees. That's definitely what's going to happen. I said that Remy's algorithm operation doesn't quite work, but an operation that works and that is compatible with growth face by face in the sense that I explained is just leaf erasure in the corresponding tree. So it so happens that if I pick a leaf and erase it in the tree, this does correspond to a face collapse in the corresponding quadrangulation. And let me also comment on the fact that there is a definite direction there. So not all face collapses are leaf erasures, but all leaf erasures on the plane trees correspond to leaf collapses on the left. All right, so as a matter of fact, we'll be able to build a growth scheme for plane trees that has leaf erasures as the core operation, and that will give us a growth scheme for pointed quadrangulations, which of course is also a growth scheme for non-pointed quadrangulations, because they can just choose the pointing at random and then forget it. It's fine. Now, in order to build our growth scheme for trees, something that, at least for now, is not wholly necessary, but is convenient and a nice way to look at it, is to think of plane trees instead of as plane trees, as binary trees. So a plane tree really is a full binary tree, essentially, because they're just constructed in the same way, right? They satisfy the same sort of recursion. And indeed, just to see how the correspondence goes, so we can say that a plane tree with just one vertex would correspond to a sort of degenerate full binary tree with just one vertex. And then we can build a bijection inductively by saying that a plane tree with at least one edge is essentially two plane trees, right? The plane tree of the descendants of the leftmost child of the root and the plane tree of everything lying to the right of the leftmost child of the root, and those will correspond to the two full binary trees of descendants of the left child and the right child of the root in the world of full binary trees. All right? Yes, just tiny comment. I'm sort of forgetting that there are colors involved. But notice that that is no problem, right? Because my leaf erasure procedure, okay, if I can grow plane trees, I can grow 3 colored plane trees. I'll just grow a leaf according to my growth scheme from a corner somewhere and sample the color of the edge I've added uniformly at random among the 3 possible. So I'll be sort of forgetting about colors of edges in this passage from middle to right there. Okay, now why was it convenient to think of things in terms of binary trees? Well, for one thing, so I need an operation that will correspond to a leaf erasure in the corresponding plane tree. And an operation that works is sort of the obvious leaf erasure in the binary tree, where what I mean here is I'm allowed to erase a pair of sibling leaves, essentially. And the opposite operation here is very natural. Growing the full binary tree would mean choosing a leaf of the full binary tree and growing 2 children from it. So that's how it works. A leaf erasure here is indeed a leaf erasure in the plane tree because of the construction I explained. And again, it went in that direction. It doesn't go in the opposite direction. All right, so why did I like binary trees to begin with? Well, because now I can probably make my growth scheme recursively, right? So now I've written it in terms of reduction, but I will exchange between growth and reduction quite often. It's just the same. So if I want to reduce a uniform full binary tree, probably sounds like a good plan is just, so I will choose whether to reduce its left subtree or its right subtree with probabilities, let's say CAB and 1 minus CAB, where I'm hoping to be able to choose this probability CAB in such a way that it only depends on the split of the sizes of the left and the right subtree. So conditionally, on the tree being of with subtrees of sizes A and B, I will reduce into one of the 2 subtrees with these probabilities. And in order for this scheme to work, these CABs need to satisfy some conditions. And in particular, I feel like maybe the easiest way to explain the equation that you get is just, okay, so take the probability that a tree of size n is split as AB. Well, that needs to be the probability that a tree of size n plus 1 is split as A plus 1b times the probability that I go and reduce its left subtree plus corresponding probabilities for the right subtree. Right? So these are the equations that these quantities need to satisfy, and of course they need to be between 0 and 1. Simplifying this expression a bit, a nice way to express it is just this one. This is the equation, and if you want, it just follows from our description in terms of a collection of functions for growth scheme for full binary trees, and from our probabilities CAB, that is what the expression for the function fn would be. And the equation for CAB that we've written there is essentially equivalent to condition 3t at this point. We could have obtained it from there. All right, now it so happens that these cardinalities that are involved are just Catalan numbers. So they're super easy. In this situation, everything is so explicit. This equation is easy enough that if you want, you could actually compute some CABs, and you'd be able to write explicit rational functions for them. And so this way, you would obtain a growth scheme for full binary trees that will give you a growth scheme for plane trees And in turn, that translates into a growth scheme for quadrangulations. So we've done the initial task that I had set for us. Hopefully it's clarified how also the rest of this talk is going to work. So what would be the next thing you attempt if you were me? Well, I think probably 2p angulations. Let's move on to a bit more general sizes of faces, but let's not try something too hard just yet. So let's remain in the world of bipartite things, where we'll be able to replicate more or less what we did so far. So with 2p angulations, I won't spend too much time on this, but you can still define face collapses just as before. So for example, I could choose this face and just zip up its boundary, glue it onto itself so that that face disappears, and identify some of the vertices, for example, like that. As a matter of fact, I will simplify my life a little bit in the sense that in this case, we did define face collapses before for faces that have other faces inside of them. In this case, it's a bit more complicated, right, to do the definition and decide where to put the faces inside. So I just won't define face collapses for those. I will say that those can't be collapsed, because as a matter of fact, the growth scheme that we just built for quadrangulations actually does not do that. It does not use those face collapses, so let's just ignore them. Although what's important is that we do need to define face collapses for somewhat degenerate faces, those that have trees inside of them. And for those, I will just think that my face collapse happens by erasing all the tree stuff that's inside the face and zipping up the boundary. The boundary is going to be of even length necessarily, so I can just zip it up somehow. Okay, so what takes the role of plane trees in this case? Well, many of you, in fact, all of you know, because we've seen that in previous talks. So you can have a corresponding version of a bijection for 2p angulations. Let me comment again a tiny little bit on this. These are, so perhaps I'm not using exactly the same notation as Boutier di Francesco Guiter, that's where we're going. But let's say that I'm considering p mobiles, where each face of the 2p angulation corresponds to a building block of a tree-like structure. The building block is no longer just an edge, but it's a graph that's a star with one central black vertex and p arms, p edges that connected to white vertices. And out of these, so like this thing, out of these building blocks, you build a tree-like structure by attaching them via white vertices only. And as usual, there are labels involved. So in this case, this is a 6 angulation on the left, and on the right, the black vertices have degree 3, so p equals to 3. You need some coloring, but you can still do it. So on the left, I'm again taking a pointing, and on the right, I can color the black vertices of this p mobile, which, by the way, I didn't mention, but it's rooted in a white vertex. Okay, I need a bit more creativity with the colors, because the colors are 2p minus 1 choose p this time. But all right, so we again have a correspondence that is between pointed 2p angulations of the sphere and colored p mobiles with an extra spin again for the direction of the root edge. So similar to what we discussed before. And again, beautiful explicit enumeration. All right. You probably won't be surprised what the operation is that we consider on colored mobiles. It is leaf erasure in the sense that now a leaf is one of those building blocks where that is attached to via only one white vertex. So essentially one of those star graphs, okay, I can't really do this, but where all white vertices but one have degree 0. Okay, a leaf in terms of the tree of black vertices. All right, that is still a phase collapse. And now, what's the next step corresponding to the one we took earlier? So a p-mobile, this time, is essentially a full p-ary tree, if you think about it. Again, it's constructed, those two types of objects are constructed in the same way. And the inductive correspondence, inductive correspondence is constructed a bit as before, right? I was saying that, okay, correspondence with full p-ary trees by considering, so the bottom leftmost black vertex, right? This will have p-1 children, and I can consider the submobiles attached to each of these children. In this case, this orange left submobile. The second one is actually empty. It's just the root vertex. And then the p submobile is everything that lies to the right of the leftmost black vertex. So this bit here, right, will correspond to the third subtree to the right. Okay, so hopefully it's clear more or less how this works. And so again, leaf erasure in the full p-ary tree, that is erasing, well, small families of p sibling leaves, corresponds to a leaf erasure in the colored p-mobiles. And this is by the way, it's getting harder. You don't see it because I'm not proving anything, but it's a bit harder to prove that leaf erasure there corresponds to a phase collapse in the two p-angulations. All right. And now, for now, I will just call up the Luxac and Winkler result as sort of a black box. Their result, a bit translated, refers exactly to the existence of a growth scheme for full p-ary trees with exactly this growth operation. All right. So for now, let's just use their result. That will tell us that we have a growth scheme for full p-ary trees. That will give us a growth scheme for p-mobiles and therefore colored p-mobiles and therefore pointed 2p angulations and therefore 2p angulations. All right, so this is the result that we have with Alessandra. Okay, so now I want to take one further step out of the coziest sort of comfort zone, that is bipartite things. And now the next thing I want to try to show you how to do is simple triangulations. We've leveled up, we've gone on 2 quests already. Let's see if we can tackle a third. So simple triangulations, again, won't define that sort of stuff. I will write that for simple triangulations of size n, where here, well, notice that simple triangulations have an even number of faces. So size n this time will mean with 2n faces, and again, rooted as usual. Now I need to change my face collapse operation a little bit because I need to collapse 2 faces at a time this time around. And so this time my face collapse will be choosing an edge, right? And collapsing the 2 faces adjacent to that edge by identifying the 2 endpoints of that edge. So something like this, right, happens. Okay, other small comment. This kind of operation does not necessarily yield a simple triangulation. The triangulation could cease to be simple, but the operations that will be involved necessarily will be just pair of faces, collapses is what I'll call them, that from a simple triangulation yield a triangulation that is still simple. All right, so we've also seen this bridge mentioned before this week. There is a very nice bijection involving simple triangulations and objects called blossoming trees, although here maybe I should be a little bit more specific because what I will call blossoming trees is perhaps not exactly what has been called blossoming trees before. So given a rooted triangulation, you can build a blossoming tree of size n that is a tree on the white vertices there with n white vertices, where each white vertex grows 2 blossoms that are the light green vertices. And blossoms are just leaves. They don't grow anything, okay? And the way I'll be rooting these blossoming trees is in a blossom. Okay, so a blossom is the root. If you want a proper bijection, here you need to start being a bit careful and you need to start talking about balanced blossoming trees. And you will need some conditions on where those blossoms are. But I don't want to have to deal with that. And as a matter of fact, I don't have to because we can do something like what we did before. More or less enumeration we can do very well still, so we're still in a very nice situation. We can do something like what we did before, so this Poulalon-Scheffer bijection, we can in fact just use as a 2 to 2n correspondence, where this time the 2n to the right is because I'm considering all blossoming trees instead of just balanced blossoming trees, and the 2 to the left is again a matter of choosing the direction of the orientation of the root edge. So this is the link in this case. I hope it's clear what a blossoming tree is. You're not complaining, great. And this time, again, things I won't show you, but they get a bit harder. And we can still do leaf erasures in a sense. And the sense in which we do it is erasing a leaf in terms of the tree of white vertices and its 2 attached blossoms. And it's a bit trickier with the correspondence, but it's okay to show that a leaf erasure in the blossoming tree corresponds to the collapse of a pair of adjacent faces in the triangulation. But even once we've done this, we've been good. But how do we grow or reduce blossoming trees now? And it's not too clear how to do something like what we did before, but it turns out that we sort of still can. So the first thing that I'll do, maybe I shouldn't have already done that, but oh well, is our blossoming tree there on the right. We can decompose it into 2 sub-objects. So I had my root that was a blossom. I can take the tree of everything descended from the root after the root blossom and before the other blossom, and then everything that lies to the right of the non-root blossom attached there to the origin, right? So I've separated into two things. And let me give a name to this type of object. I don't know, maybe it has a name, but I'll call it potted blossoming trees, let's say. So those are potted blossoming trees in the sense that they're blossoming trees, but where their root, which is now a white vertex, doesn't have any blossoms. But now, if I look at a single potted blossoming tree, that can be decomposed into 4 potted blossoming trees that are smaller. I can consider the potted blossoming tree obtained by looking at the leftmost child of the white root and all of its descendants lying to the left of the first blossom. Then the subtree that's issued from the leftmost child of the root and lies between the first and second blossom, and then one that lies to the right of the second blossom. And then finally, there's a 4th potted blossoming tree that is everything from the root that lies to the right of the leftmost white child of the root. And so as a matter of fact, each of these 2 potted blossoming trees I have constructed as a full 4-array tree, right? This is again, same recursion. You can very quickly try to think, so I've rotated the other 4-array tree so that it goes from top to bottom. If you try to reconstruct how the bijection would go for the right potted blossoming tree, well, the decomposition that I've described to you before would be this one. And so you have this correspondence. And what's nice again is that leaf erasures, in terms of these 2 full 4-array trees in the way that we defined before, still correspond to leaf erasures in the original blossoming tree. And notice that the construction I've described to you also gives you a 2 to 2n correspondence between simple triangulations of the sphere, rooted, of size n, and objects on the right that, if you like, I could describe as rooted plane trees, all of whose vertices have degree 5 or degree 1. So that is what the object on the right is, and that gives you potentially a bijection once you iron out a couple of things about what I mentioned so far. And so just to finish, I don't know how long I have, more or less, but...
You have 5 minutes.
Okay. So we'll go through this quickly because we've done a lot of working preparation, so this should not be too difficult. So now we know how to grow 4-array trees, right? That's fine. Lukszak and Winkler tell us how to do it. And this time we have to decide how to grow or reduce each of those 2 4-array trees of the pair. So I need to choose whether I reduce in the top tree or in the bottom tree. And again, I will choose to do it with probabilities that only depend on the split, on the sizes of the 2, and that satisfy the correct equation that is built similarly to the one you've seen before. And what I wanted to do in the very last 5 minutes, but we'll see whether I'm able to, is give you an idea of how you'd actually go about finding these probabilities. And I thought that would be useful because that's also an idea of how the Lukszak and Winkler proof works for showing that there exist these growth schemes. And the sort of argument that we have to make is a max flow min cut type of argument. So the sort of problem that we're faced with, now what we're trying to do is decide whether to, let's say, grow in the top 4-array tree or the bottom 4-array tree. I'm building a corresponding flow network where the first column corresponds to all the possible splits. So the first vertex would correspond to all blossoming trees that have a 4-array tree of size 0 on top and one of size n-1 on the bottom, and then size 1 n-2, and in general size a n-1 minus a, right? Okay. For the first column, and the second column will be one larger blossoming trees with all their splits. Okay, now I have this flow network. I need to choose capacities for my oriented edges, and the sort of capacities you need to put. So for example, for vertex A on the left, I put as a capacity of the edge joining the source to that vertex the probability of a blossoming tree of size n being split as a n-1 minus a, right? And I'll do the same for the right. So for example, the capacity of the edge from a+1 to the sink will be the probability that a blossoming tree of size n+1 has split a+1 n minus a+1, be the right thing. Okay. So just to help you visualize, let me say that, okay, these capacities allow a certain amount of flow through these edges into the blue dots, and I've drawn them larger or smaller, sort of according to, well, their actual probability, which is the amount of flow that can go into them on the left and can go out of them on the right. All right, and for the middle edges, I will just put infinite capacity. That is no constraints, okay? And now I hope you're kind of convinced that what I'm looking for in terms of this flow network is just a unitary flow on it. So I want to split my probabilities on the left in towards the right via the arrows that I've drawn that are exactly those where growth is allowed with my growth operation, in such a way that all of the allowed mass, that is 1, flows through this network from the source into the sink. And perhaps this is supposed to be the end, so I won't talk too much about what a cut is and how the max flow min cut theorem goes. But so you have a simple, quite elementary theorem that tells you that you can know what the maximal flow that you can move through this network is in terms of the minimal capacity of a cut. And now the capacities of the edges are very explicit. So here I was giving you examples of cuts, but I won't say anything. This is the theorem that I mentioned. And now the problem becomes, are we able to show that a minimal cut has capacity 1, and that's it. And what you're able to do is essentially show that the cuts with minimal capacities have a specific type of shape. They have to be consecutive in some sense. And then even now, I mean, these TA4, etc., are explicit quantities that you can write down. The important fact that you're going to use, as a matter of fact, is that cardinality of TA+1, 4 divided by cardinality of TA4, which you know converges. This is increasing in A. And this is the key fact that allows you to show this first lemma and at that point, the fact that among all these cuts, the minimal cuts have capacity 1, which is what you wanted. And therefore, there's a unitary flow through the network. And now you can use the Lookschak and Winkler result, which you can think of as some inductive version of what I just showed you here, where you have to do multiple layers in order to do p-array trees or d-array trees. In this case, you just need 4-array trees. And you obtain a uniform growth scheme for quadrangulations, which is what we did with Alessandra. And thank you very much for your attention.
Thank you for this colored talk. Are there questions, Nicolas? Jokes are just after the questions. You okay?
Sorry?
Jokes
is included in the question.
Okay, good. He was first.
Okay.
Okay.
Thanks a lot, Alessandra, for this wonderful talk. One question and one comment. So this growing scheme for a random tree, you can ask if there is some convergence as n goes to infinity in the local or global sense. Do you have an answer to that?
Yeah, so at least in the local sense, I do, and it's in fact already in the paper by Lookschak and Winkler. They do describe that essentially you'll see, well, the
local sense
tree in the d-array tree version, of course. But yes, it's so, and you could, in principle, and I'm interested if any of you have related questions, because this result is quite new, but I think one could think about it a little bit more. Of course, you can think of this in terms of the maps, so the quadrangulations and what happens and how that relates to the UIPQ or the UIPT, how fast balls are revealed, and all sorts of questions like those. And as you've seen, the final results of this growth scheme, the probabilities, are not quite explicit, but that doesn't mean that you couldn't use certain parts or estimates to obtain actual results about what happens.
And the second one is a reference and a joke, which is, I think, particularly appropriate in your case. There is a work connected to that, a work of Luigi Adario-Berri, entitled blah, 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 Growing Maps or whatever, or Comment s'enfuir de l'hexagone, within the title. So you should have a look to see how to escape from hexagone. Thanks.
Jean-François.
In fact, it was essentially the same question as Nicolas, but in the global sense, meaning that you can construct, for instance, a sequence of triangulations with n faces, and can one expect to have now an almost sure convergence to the Brownian map when you take the scaling limit?
That is an example of a question that, I mean, it's fair to ask, but I don't have even a strategy to go about doing that for now.
Okay, thank you.
Do you know what happens when you remove an internal vertex? You remove an internal vertex, all the trees above it, what happens?
You want to remove, okay. Well, I mean, yes, that would be a larger sort of a block operation with a collapse of a larger portion of the quadrangulation. Something that maybe I can comment on related to that is, of course, and it's related to Remy's algorithm, you might think of collapsing internal edges erasing internal edges and leaves of these tree-like structures. But this doesn't work that well with respect to single face collapses, which is what I'm trying to do. Because what actually happens when you collapse a face is that indeed you collapse an edge, but then normally there's a subtree that gets moved somewhere else in the tree. And that's why it works well if you're dealing with leaves, because those don't have a subtree that then starts moving somewhere else, right? But what you said was collapse not just the edge, but the whole subtree, and that, yeah, probably is kind of a face collapse, but a larger, boundary, and then you collapse all the faces inside it, something like that.
Thank you.
Thank you again for this nice talk.
Thank you.